So our problem statement for today is where we are going to build a machine learning model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. So we have about 9,568 hourly observations. So this is a continuous data in form of temperature, ambient pressure, relative humidity, and the exhaust vacuum, which all in all have a combined influence on the net electrical energy output, which is a target that we're trying to predict. So here, our approach would be to use supervised learning since we have a set of input data and target variables to train our model, and then we'll be testing it on unseen data in our testing phase. So our input features are the temperature, ambient pressure, relative humidity, and exhaust vacuum. So here, initially what we'll be doing is we'll be using correlation to find out the most influential features. Then on, we'll combine features in a group of three and in groups of three, in two groups of three, and finally in all features against the output and use multiple regression as an algorithm to see their influence on the target variable. So we'll be splitting the data into 70 for training, 20% for validation, and 10% for testing. The output metrics here in this case we have chosen are the mean absolute error, the mean absolute percentage error, and the mean squared error. So let's move on. So this is our master data set that we've taken. We've split it into the training, validation, and testing data set. Now we're analyzing the relationship using correlation to find out which features have a strong influence on the final output. So as we can see, ambient temperature and the exhaust vacuum have a strong negative effect. The ambient pressure has a positive effect. The relative humidity has a mild positive effect. So based on this, we'll be splitting them into model 1, 2, and 3 as shown on the screen. So here we are training the model based on the training data set as shown below. And we're using the data analytics tool built in Microsoft Excel to perform this exercise. So what we've done here is we've trained this data and we've found out the output metrics, which are the MAE, the MAPE, and the MSE. So this is what we found for model 1. For model 2, this is the MAE, the MAPE, and the MSE. Similarly, for model 3, as we can see, so for model 3, it is 3.59, 0.0079, and 20.16. So this is what we've got output from the training of these models. Now, we wish to compare how they fared in training. So we've compared these against each other in training, and we could see that output from model 1 was showing the highest amount of error. But this is just the training. So what we're going to do is we're going to perform the validation on these models to validate our training evaluation. So using the validation data set, we've found out the MAE, the MAPE, and the MSE for model 1, model 2, and for model 3. Now, since we have trained it and validated it, so now let's see if our training evaluation was correct. And yes, it is correct. Model 1 still continues to show us the highest amount of error. Since this model 1 has the highest amount of error and that too by a large margin in the MAE and the MSE and also in the MAPE, what we're going to do is we're going to eliminate this model. We're not going to test this model further because this model requires a lot of work to be done on it so that it comes at par with the performance metrics of model 2 and model 3. What we're going to do instead is to take the two remaining models which have performed better than model 1 and test them to see if they're still better and to find out the best model from our unseen data test in the testing phase. In the test phase, we've tested the model 2 and model 3 on the test data, which is unseen data. So this is the MAE, the MAPE, and the MSE E for those. So this is the output for the MAE, MAPE, and the MSE for Model 3. Now let's come to comparative evaluation. Now, as we can see, in testing, Model 2 and Model 3 are pretty closely matched, but Model 2 still has the lowest mean absolute error and mean absolute percentage error. But Model 3 has the lower mean squared error by just a very small margin. Now, let's draw a conclusion based on these output metrics. So as you know, we've split them into three models. We've checked the models in training, validation. We also eliminated model 1 after training and validation because it produced the highest error. Now, since model 2 and model 3 were pretty closely matched throughout training and validation, we decided to proceed with them to see how they performed in testing as well. Now, post-testing, we've seen that model 2 has a lower mean absolute error and mean absolute percentage error, but has a slightly, very slightly, a higher MSE value than model 3. Now, the thing with mean squared error is that it has a characteristic to capitalize heavily on outliers in the data set. This is a significant help when we are trying to identify large errors in our data set. But what it does is that it is influenced by the scale of the data. Now, the data that we're dealing with is in the magnitude of thousands. So what happens is it is capitalizing on the outliers as well, and also the scale of the data is influencing it. So we could draw a conclusion that MAE and MAPE values could be a better output metric for comparing these models at this juncture. So model 2 has slightly lesser MAE and MAPE values, which give us a better idea of the performance of model 2. And the model 3, which has a slightly lower MSE, is also very close to the MSE value of model 2, which could lead us to conclude that model 2's performance can be rated as optimal for the current problem statement, which makes it a suitable model choice in this case.